Gnanam Paramam Dheyam. Knowledge is supreme.
Right. So, like I was saying in the last lectures, that we want to study polynomials, the zeros, and also the groups together. So let us start with the polynomial f. F is a polynomial with coefficients in a given field k. K is the field. And then we know now that every field has an algebraic closure. So, usually an algebraic closure of K, this is denoted by K bar, and we fix it. We fix that for, like in one of the last lecture I commented that if you want to study this, we will fix this. It is unique up to a K algebra isomorphism, but it may be different, it's not equal. So, therefore, we fix it, that one, and therefore, in that field every polynomial with coefficients in K will split into linear factors. So, therefore, f will split, f may be some constant, x minus x1, x minus xn. This splits into linear factors where this a is actually in the base k, and x1 to xn, these are the zeros of f, all zeros of f in k bar. All of them lie in k bar, and these are all, maybe some of them are repeated, etc., etc. But to this f, we are therefore we are writing this notation v of f. We have been writing this, but this is all x1 to xn, and this is a subset of k bar, and these are called a zero set, zeros of f, zeros of f, without saying where. It is understood that it is taken in k bar. So, here also I could have written k bar, but when I do not write, that is, it is assumed that it is in k bar. In earlier lectures also, that was the strategy. And we know, therefore, fundamental theorem of algebra says that the number, this number, that is cardinality of v of f, this is bounded by the degree, and this is crude. So, if you take them distinct and compute according to the multiplicity, then also it will be exactly equal, but I do not need it right now. So, we have the zeros and we want to study the zeros. So, note that the zeros, we have seen in one of the earlier lectures that the zeros and embeddings. So, if I want to embed, so home K algebras of Kx mod f, Kx mod ideal generated by f in some field L, field extension L, these are precisely the zeros of f in L. This we have seen, there these two sets are bijective. There is a bijection between this. So, if I would have taken L equal to k bar, I will take here all zeros. So, alright. So, this is it. Now, to this f, we are adjoining, therefore, we are associating a subfield of k bar, that is generated over k by the zeros of f. So, this is x1 to xn. This is a subfield here, and not only that, this is a finite extension of k. So if you call this as L, L over K is finite extension, finite field extension of field extension, and at the degree also we know L over K degree is smaller or equal to n factorial. This is also clear. This you do it by induction. First I would simply say here, check this. So we got a finite field extension of degree less equal to n factorial. So therefore, to this F we have attached the field extension L over K, where all the zeros of F, they are contained in L, all zeros. In fact, L is generated by over K as generated by V of F. Is the smallest subfield of the algebraic closure which contains all the zeros. So therefore, we have a Galois group, Gal L over K. And also we know that this L over K, this is a splitting field. This is a splitting field of F, the polynomial F over K. Therefore, L over K is normal field extension. What is the definition of normal? Let me recall quickly. So we say that the field extension L over K is normal if I take any embedding, K embedding, if every K embedding from L to where an algebraically closed field, but that is I am taking K bar now. K bar, every embedding maps L inside, maps L into L. So that is sigma of L is contained in L. That is the normality definition. Alright. So that is this field, the field extension is normal, we know. I also want to say that we can also assume we can, to do this, whatever we have done, we started with any polynomial f in Kx. I wanted to claim that we may assume that f is a separable polynomial. So what is a separable polynomial? It doesn't have a repeated zeros. Zeros are distinct. But you see, that I can achieve by so we have f was arbitrary polynomial in Kx, and this f, therefore, because we know every this polynomial ring over a field is a UFD, so therefore this f, definitely I will factor the prime factorization of f in Kx will look like this, some constant pi 1 power nu 1 pi r power nu r, where this a is actually constant in a, nu 1 to nu r are non-zero natural numbers, and pi 1 to pi r are prime polynomials in Kx. That is the prime decomposition of f in Kx. And as far as the study of zeros, V of f is same thing as V of pi 1 union V of pi r. And this is same thing as V of pi 1 to pi r. So I could have simply replace F, this was F, replace by F red, reduction of F, it is called reduction of F. This is simply pi 1 to pi r product. This is called reduction of F. This is also a polynomial in Kx only. So our zero set did not change. And then now the splitting field will also not change, because all the zeros split, so L over K is the same. This is the splitting field of F or F red is the same. All right. So this will we can assume always in the study. We will always assume the polynomial is separable, or polynomial at least separable. I will have not done very formally yet, but we may assume that F is a product of distinct prime polynomials. That is what we will assume. So going back to F, I have attached a finite field extension L over K. Finite field extension and we have the Galois group. This Galois group, I want to call it a Galois group of F. And I will therefore denote by G or Gal F over K, or sometimes I will simply write GF. And to study the zeros of the F, I will study this Galois group. So for example, I will write down what are the orbits, I will say what are the stabilizers and so on, so that group action. All right. And also we know that the most important observation we have used so many times, important observations. This we have used so many times. G gal Kf operates on zero set of F naturally. So what is the operation? This is my set where this group is operating. So gal Kf cross Vf to Vf. What is the map? Take any sigma and take any 0 of F and map it to sigma of x. So this is a 0 means f of x is 0, and we are applying to this sigma. Sigma is a ring homomorphism, so sigma of 0 is 0. And also it is k-linear and it respects the multiplication, therefore this is nothing but f of sigma x. That means sigma x indeed belongs here. And it's clear that if sigma is identity, this is x only, and if I have sigma and tau, and then so it's a group operation. This is a group operation. Okay, so our aim will be to study this group action more and more intimately. Okay, before this we will do it in coming lectures, but I want to remind you that we need to prove something about the splitting field, which I have not formally proved it. So what is that thing I want to prove? That if I have, so we need to prove the uniqueness of splitting field. And what should uniqueness means? Uniqueness of splitting field of f, a polynomial f. So what is that? Why is it necessary to prove? Remember what we have done. We have a field K and a polynomial f in Kx, and we have fixed an algebraic closure. K bar is an algebraic closure of K. And now we have chosen, we looked at the zero set here, Vf is here, and the splitting field is L. L is K of Vf. But see, this is a finite extension of K and it is a subfield of K bar. So somebody changes K bar, somebody picks up another model for the algebraic closure, then one will come across some other L prime. So L prime. So if L and L prime, with this preamble, if L and L prime are two splitting fields of f, then we should prove them they are isomorphic over K. Then L and L prime, there is a K algebra isomorphism. Iso. This is needed to prove. Okay, let me indicate the proof of this. Already we have proved it, but I only have to tie the things. So, proof, uniqueness of splitting field of a polynomial f in Kx. So that means we want to prove that if I have, so suppose L and L prime are two splitting fields of a polynomial f in Kx over K. Then we want to prove, that there exists a K algebra isomorphism from L to L prime sigma. This is what we want to prove. Alright, but for this we are going to use, so we will use what we did about, so we will use the following observation. This is from extensions of embedding. Of embeddings. So what I want to use is the following assertion. So whenever I have an intermediary field of the finite field extension M L over K, and suppose I have a K embedding of L in an extension E of K, this is K embedding, then there exists a finite field extension E prime over E, finite field extension. So E prime over E, you can find this finite extension, and in this sigma I can extend it to this sigma prime. So sigma is extended to a K embedding sigma prime from L to E prime. This is what I want to use in the proof. So, how is it used? So, we have L here and we have this is a splitting field L of this is a splitting field of a polynomial f in Kx, okay, and L prime is another splitting field of the same polynomial. Now, we take this natural inclusion map as an embedding, and now this is, so this says that this embedding I can enlarge this field L prime to E prime. This is a finite extension, so that this natural inclusion map is extended here. So, that I want to call it sigma. And similarly, interchanging the roles of L and L prime, we have an embedding. So, similarly, we have a tau, So, similarly, we have a finite extension E over L such that there is a K embedding tau from L prime to E. Now, note that this, because this L is a splitting field, this image of, so since L is a splitting field, of f, sigma of L is actually contained in L prime. That is because all that you have to check that is, for this it is enough to note that if x is a 0 of f, then sigma x is also 0 of f. And similarly, tau of L prime is contained in L. Same observation. This observation is so very important, we have used it several times in the course. Namely, if x is a 0 of a polynomial, then, and if a sigma is an embedding, then sigma of x is also 0 of the same polynomial f. So, all these together shows that if I take L over K, this degree is smaller equal to this is the degree is same as sigma L over K, but this is smaller equal to L prime over K, because sigma L is contained in L prime, and by the same argument this L prime over K is smaller equal to L over K. This is interchanging the roles of L and L prime. So, because of this and this is equal, therefore, all are equals. So, that shows that sigma L is actually L prime, and similarly tau of L prime is actually L. So, in other words, the sigma and tau, so that is sigma and tau are K algebra isomorphisms. So, that proves that L and L prime in particular they are isomorphic over K. So, we have proved that any two splitting fields are isomorphic. Note that these sigma and tau are isomorphisms, but they may not be inverses of each other, because we we have there is no connection between sigma and tau, because the sigma and tau are obtained by extending the natural inclusion, and that may not be compatible with each other. So, therefore, we cannot say that sigma and tau are inverses of each other, but definitely sigma and tau are isomorphism. That is what we wanted to prove. If you have a splitting field of a polynomial, single polynomial, it is a finite extension, and this finite extension is uniquely determined up to a k isomorphism. Therefore, the group we have attached to that is isomorphic. So, therefore, when we fix algebraic closure, there is no ambiguity, because the algebraic closure are not equal in general, but they are isomorphic. For this reason, I had to make this remark, and this I should have made it actually that time only, that when we studied zeros and embeddings of a field. Okay, so with this, now from next time onwards, we will concentrate more on studying Galois groups of a given polynomial, and this given polynomial will give you field extension, and in order to achieve better results, we will have to assume the polynomial is separable. Right now, we only are assuming that the polynomial is a product of distinct linear factors, distinct prime factors. So, but now it might happen that the prime factors may be separable or not, that we have to analyze. For this reason, next time I will define what is a separable field extension, and then we will analyze when an irreducible polynomial will be separable or not. And normally the problems will not arise in characteristic 0 fields, but when the characteristic is positive, then the many problems may crop up, but that we will have to carefully study and decide when can an irreducible polynomial be separable or not, or what are the examples of non-separable polynomials. Okay, this we will do it next time. Thank you very much.